Hi everyone, today I want to talk about an approach that learns correspondence between robots in a weakly supervised manner. Imagine a setting to learn a policy for a high-degree freedom robot like a Franca arm, but we only have demonstrations from a lower-degree freedom robot like a UR5E arm. Due to the different structures, it is difficult to directly imitate the UR5E arm's behaviors. However, humans are born with the ability to develop new skills by mimicking the behavior of others with different embodiments. Can we imitate the behavior of a robot with different embodiments by building a correspondence between the two robots? Prior works on correspondence learning can be roughly divided into supervised learning and unsupervised learning methods. Unsupervised learning methods mainly leverage inductive bias to learn the correspondence, while supervised learning methods use a dataset of paired state-action pairs with the correspondence. Both methods have advantages and disadvantages. Unsupervised learning methods have low annotation effort but also suffer from low accuracy, while supervised learning is on the opposite. Thus, our key insight is to find a trade-off between supervised learning and unsupervised learning using a method that requires little annotation effort but also can introduce a more accurate correspondence. Let's take a look at an example. Two different ant robots give two trajectories. Here, given a pair of states, annotating whether they are aligned can be difficult. However, answering if they have the same location on the 2D plane is easy. In this example, the location of the agent is an abstraction of the state, which describes partial information of the state. We define the space of abstraction as Z and define the abstraction as a mapping of the state-action pairs are only the states from both domains to the Z space. The abstraction function is defined by the designer to make sure it is easy for the labeler to describe similarity in the Z space. Thus, in this paper, we are given trajectories from both robots and weak supervision in the form of paired state actions or states along with their similarity. Our goal is to learn both the abstraction functions as well as the correspondence maps. We build our method on top of the state-of-the-art unsupervised learning method, DCC. Similar to DCC, we also learn a state mapping, a forward action mapping, and a backward action mapping. We adopt all the losses in DCC but further embed our weak supervision into the correspondence learning objective. We model the abstraction and the similarity as a neural network, which consists of two encoders and an MLP. We get the similarity value by similarity functions. Then we adopt the quantity loss to learn the similarity functions. We minimize the negative similarity value between the states or state action pairs before and after the mapping, which ensures the mapping keeps the similarity. We conduct experiments with the different environments varying morphologies and modalities. We first conduct experiments on different morphologies on the ant environment where the two agents differ in the number of legs. We use the location of the agent as the abstraction. Here we can observe that our ant moves faster. For the cross-modality setting, we conduct experiments on the real robot environment. We aim to build correspondence between an environment using the third-person view image modality as the state and another environment using the joint angle modality as the state, while the two environments share the same action space. For the abstraction, we use the location of the ant effector, which can be easily estimated from the image and directly read from the joint state. We test the correspondence by a task of moving the book across the shelf full of books. We can observe that our method finishes the task. Here is our conclusion. Thanks.